My name is Claudio. I work at IBM, and I'm here to present this VTPM, Virtual Trusted Platform module. We've been working for Confidential VMs, and we call it Zero Trust because it has to follow the trust model of a confidential virtual machine where we cannot trust the hypervisor. This is the outline of the presentation. So I'll give you an introduction and walk you through how of the problem we are trying to solve. Give you some background on attestation, and also and then discuss about the VTPM we are working on. Discuss some design topics and also the architecture. If we have some time, I'll give you a demo and leave some time at the end for questions. Okay, so when an application have sensitive data, we need to protect the sensitive data. The application needs to protect the sensitive data end to end. It means at rest, in transit, while it's in the network, and also in use, while it's in memory. For the first two, at rest and in transit, there are solutions that relies on basically cryptography. But for in use, we need to rely not only on software, but also in hardware. And that's where this trusted execution environment technologies try to address, try to solve, protect data while it's in use, which it's basically create an hardware isolated environment where you can put your application there and run it. TE technologies, they can be applied in different levels. We can apply them in a process level, and more recently there are technologies, TE technologies, that allow us to apply them in a virtual machine level. So we can create an enclave and add your virtual machine inside that enclave and run your virtual machine. When we say that, when we have a virtual machine inside of an enclave, we usually say that we have a confidential virtual machine. And these are the technologies that support that currently. SEV-SNP, for example, actually, Intel DDX, ARM CCA. And as I mentioned, all these technologies, they protect the VM data while it's in use from unauthorized access. And in this case, we are more concerned about hypervisor and also cloud service providers. Confidential virtual machine has been explored in multiple use cases, such as cloud, I/O, and multi-party computation. When it comes to consumption model, when we launch a confidential virtual machine, usually first customers want to attest if that virtual machine, if that confidential virtual machine is really exactly what you expect it to be. It's in the state you want it to be. And it has not been tampered with. But then it brings a question: how do we attest a CVM then, a confidential virtual machine? And the idea is similar to the one we have in the host. We use measured boot with attestation tools. And measure boots, we need to measure not only the boot, but also runtime. And for confidential virtual machines, we can request a VM launch measurement, which covers basically the initial state of the VM. But then it's not enough if you want to do attestation, because we need to measure every subsequent module that is loaded after this initial state. And there are solutions up to the guest OS. There are solutions proposed already, but they are not standard, and they also rely on untrusted entities. In the last KVM forum last year, Tobin and Dov started discussing that, how we could have a more standard way of attesting a confidential virtual machine. And we believe that using the trusted platform module is a good way of doing that, because the TPM is an industry standard for attestation, and it also already has a TPM tooling, a rich TPM tooling that we could reuse. And additionally, we could use the integrity measurement architecture, which is a more advanced technique for runtime attestation. And that was our motivation then to develop a zero trust VTPM for confidential virtual machines. And our target platform is the AMD SEV-SNP. Okay, it's about attestation. So let's quickly go through TPM-based attestation. There is this TPM. The TPM is a trusted platform module. So it's a chip. And it provides these platform configuration registers. And the way that these registers work for attestation is that as we boot a system, we take measurements of every event that could change the state of the virtual machine. And then we record these measurements in the platform registers. And there you can see the SHA-1 bank. It has 24 registers. There are other banks as well. I'm using the SHA-1 because it has small hashes. But the way that we record these hashes, these measurements in the TPM PCR is through a PCR extend operation. The interesting thing about the PCR extend operation is that it doesn't destroy the current value. It builds on top of it. So if you do a PCR extend, you need to provide a digest, and then the TPM will take your digest, read the current PCR value, concatenate both, and take a hash of this new string, and use it as the new PCR value. With this idea, what we see in the PCR values is a value, but it represents a ordered event of a series of events. In other words, an event log. And that's the idea of attestation. We can just get these PCR values and compare with the values that we expect them to be. And if they do not match these values, we can go through an event log. We validate this event log, but we can go through an event log and find out where exactly it's deviating from what you expect. And there are several tools. There are some tools that could be used for attestation. One of them is the Keylime. It's important to understand that these attestation tools, the first thing that they will do is check if they validate your TPM to see if it's an authentic TPM. And then it will do the attestation as you request later at runtime. Okay, now that we understand about attestation, for the zero trust TPM, there are some key points that we need to discuss to solve. And I'm going through each of these points now, but basically they are: where should we run the VTPM? How can we prove that the VTPM is authentic? And also discuss about the state of the VTPM, injection or ejection. Okay, the first question is, where should we run then the VTPM? The VTPM it doesn't run in a physical TPM. So we don't have the protection of the hardware, the VTPM hardware, to protect the state of the VTPM, the data, the TPM data. In our case, a VTPM is a software. It doesn't run in the TPM chip. We use the Microsoft TPM 2.0 reference. And since it doesn't run in the TPM chip, we must protect the VTPM state. We must protect the TPM data from unauthorized access, especially the hypervisor, but also from the guest OS. Based on that, there are some, initially we thought about 3 options. We could run the VTPM in the host, but it doesn't seem to be a good idea because the host kernel would have access to the VTPM data, to the VTPM memory. So another option would be to run it in a confidential VM. This seems to be a more generic approach, a more generic solution that would be easier to implement in other architectures. But on the other hand, it also brings in some complexity in terms of orchestration, because the VTPM would be running in a separate confidential virtual machine, different from the virtual machine that we are running, and every command we send, we would need to send to this separate confidential virtual machine, and also there is the probe, and the VTPM would need to be available at the beginning of the boot, at early boot. It would complicate also the orchestration. Based on that, we think that the best option for us is to run the VTPM in the confidential virtual machine that we want to attest. But still, where exactly inside that confidential virtual machine that we want to run the VTPM? And we run it in the SVSM, the Secure VM Service module. We do that because it's the first module that runs in SEV-SNP guests. And with that, the VTPM would be available for subsequent modules to take measurements and start using the VTPM. And also, because the SVSM is used to provide runtime privilege service to the guest. And if you look at this SVSM specification, the VTPM is one potential candidate for privileged service candidate to provide services for the other components. And also, we run it in the SVSM because the SVSM leveraged the VM privilege level feature from the SNP platform, which basically allow us to take the address space of the guest and divide it into multiple levels, VMPL0 to VMPL4, where the VMPL0 is the most privileged one. And since we run the VTPM here in the SVSM, the SVSM runs in VMPL0, and this way we protect the VTPM data from the other components, subsequent components, OVMF and guest kernel. Okay, but if we run the VTPM here in the SVSM, there is a change that we need to make in the VTPM drivers. Because the VTPM drivers would not talk anymore to the TPM chip. It would talk to the SVSM-vTPM. In other words, the SVSM needs to provide runtime services for the other modules, for the other software components, and also the VTPM driver would need to send the VTPM commands not to the TPM chip. It would need to send them to the SVSM-vTPM. And we worked with the community to define this VTPM protocol. You can see that in the SVSM spec 0.62, Tom, which is back there, and he sent this spec to the Linux Coco mailing list. Currently, there are two SVSM implementations, the AMD Linux SVSM and the Coconut. We are working with both of them. We started pushing push patches to the Linux SVSM, and now we started working with Coconut. The other big question is about authenticity. When we talk about the TPM authenticity, we need to talk about the physical TPM too. How can we prove that a physical TPM is authentic? Physical TPMs has this endorsement key, which is a TPM identity. Each physical TPM has its own identity. And when it's created, when the EK, the endorsement key is created, the EK, the private part of the EK never leaves the TPM. We also have this EK certificate, which basically is a certificate of authenticity for the EK. And the TPM manufacturer ships a TPM with these two, the EK and also the EK cert. The EK cert is how it, the EK certificate, it binds that EK that was generated to a TPM manufacturer, because the manufacturer will sign a certificate that contains that EK pub. And that's how it's done in the physical TPM, but how can we do that, a similar idea, for the SVSM-vTPM? It's easy to create the EK. The EK is not a problem. We can just issue a command to the VTPM and say, okay, create for me a primary key. But the first thing that we have to do before creating the EK, we need to make sure that we have a good entropy source at the beginning of the boot, because the EKs would be created at early boot, so we need to make sure that the entropy source to create the EK is good. And for that, we changed the rand function to call the platform RD rand assembly instruction. And since we are using the Microsoft TPM 2.0, it depends on OpenSSL, so we have to have an OpenSSL. The real question is, who would sign, who would give us a certificate of authenticity for the EK we just created, that the SVSM just created? We know we don't have the TPM anymore, the TPM chip, a hardware, to certify that for us. We don't have a TPM manufacturer. But we do have the platform, the AMD platform. And we can call the AMD secure processor to issue a certificate of authenticity for the EK using the SNP attestation report. When we request attestation report, basically the AMD service secure processor, it gives us back a signed attestation report that changes back to the AMD key, root key. And that's how we can also chain the have a certificate of authenticity for the EK we just created, because when we request an attestation report, it takes 2 arguments. We can pass 2 arguments. One of them is 64 bytes, and these 64 bytes will be also in the attestation report. We use that 64 bytes to pass we pass the SHA-512 hash of the EK pub in this report data, these 64 bytes. And then the AMD service secure processor would give us a certificate with this EK pub hash inside of it. But still, there is a question. How do we make sure that this attestation report was created by the SVSM? How can we ensure that the EK was created by the SVSM and not by any other software component or even other SVSM in other GAST? Well, the attestation report also takes a VMPL level. So we request a VMPL 0 attestation report. And since only the SVSM runs in VMPL 0, it's the only one that can request an attestation report for VMPL 0. Because the request is encrypted with a key that is available only in VMPL 0. This key is the VMPCK 0. And that way, we can prove the authenticity of the EK we generate in the SVSM. It would be signed by, it would be an attestation report that would be chained back to the AMD root key. And also, all attestation report requests that we do here anywhere in the GAST, it needs to be encrypted, because this request goes through the hypervisor. And the hypervisor, it would need to know, to decrypt this message, it would need to know a key that is available only for the GAST and the AMD secure processor. And that's how we protect this request from the hypervisor. it's a standard protocol available in the SNP platform. And lastly, I want to talk about the ephemeral state. Currently, on every boot, we create the EK, and then we request a VMPL0V port to bind the EK we just generated in the SVSM to the AMD hardware through the attestation report. And then we save this attestation, this VMPL0 attestation report in the TPM and VRAM, so that later at runtime we can just attestation, any attestation tool can go to this TPM and VRAM index we saved and verify the authenticity of the TPM. And with that, we have an ephemeral state for the SVSM-vTPM. We know that there are some use cases that requires persistent state, but we think that there are many advantages by having an ephemeral state, and it would be enough for doing attestation. Some of the advantages is the this ephemeral approach. It has a simple design, and it's already good enough for having runtime attestation, a TPM-based runtime attestation. And one thing that is very important is that we don't need to eject or inject state, which is complicated in this case from the perspective that we don't need to protect any state when we eject the VTPM state at a certain point in time when we want to destroy that guest. And then when we boot the guest again, we need to get that state, inject that state into the guest. That brings some complexity to the threat model, because we will need to secure the state at rest as well, and also at runtime, while it's in use. And with the ephemeral state, we don't need to do an early attestation for the VM launch measurement. Because if we want to inject the state, first we need to make sure that before injecting the state at runtime, that while the SVSM is booting, first we need to make sure, we need to attest if that launch measurement is really what we expect. And that brings complication to early boot, because we will need to have more code to do that. And with ephemeral state, we can postpone it to runtime. And also, there is no need to secure, I've already talked about that. We don't need to secure the TPM state at rest and in transit. State injection requires more code and also orchestration at early boot. For example, we may need to have some network stack at early boot. And in general, the attack surface when we have a ephemeral state is much smaller compared to persistent state. Another thing is migration from the perspective of the TPM would be easier, because we don't have states to migrate to another guest. The disadvantage is that we may have limited use cases. It works for runtime attestation, but we know that there are some cases, for example, full disk encryption, that requires persistent state. For that case, we can use, we can enable full disk encryption by having an intermediate storage key. We could generate create an intermediate storage key, and then do some sealing of the disk encryption key to that intermediate key, and have that that key in the, for example, loaded in the initRD. The process is a little bit complicated to do that, but it's possible. Okay, and this would be the SVSM-vTPM architecture. We have a proof of concept. You can go to that link and look, check, clone it, and try. But that proof of concept, it uses wolfSSL and also uses the CRB. Currently, we are not using that anymore. We tested this proof of concept with Keylime, the attestation tool. And we are contributing the SVSM-vTPM to SVSM open source projects. So here inside the SVSM, we have the core and where we have most of our contributions, because we need to integrate the VTPM, the Microsoft TPM, and also integrate libcrypto and a small libc, I would say. It's only the libc, the runtime part of the libc, and it's based on muscle. And both the core and also the VTPM depends on crypto functions, crypto support. That's why we have OpenSSL there. Currently, everything is running inside the SVSM, the AMD SVSM, and it's running in VMPL 0, CPL 0. We have, for those that want to join the discussion today in the BOF, we can discuss that, how we can better isolate all these components inside the SVSM, but using the Coconut SVSM. Okay, so how we are in terms of time? Huh? 2 minutes. Okay. Okay. So now I'm going to do a simple demo, and I want to show that when the SVSM is booting, it says that the VMPL 0 attestation report in the TPM and VRAM, and I want to validate that attestation report to see if it's authentic. Basically, we have to go through 3 steps. The first one is check if the signature is okay. We need to go to the AMD website and download the key that we expect this attestation report to be signed with, and then validate the signature. And once the attestation report is valid, we can check the content of the attestation report. We need to make sure that those 64 bytes that we use for the hash of the kpub matches with the hash of the kpub that is available in the TPM, VTPM. And we also need to make sure that this attestation report was generated in VMPL 0. In other words, it was generated by the SVSM. Following the same idea, this is a zero trust demo, okay? Here, as I mentioned, I'm booting the SVSM that I compiled from the proof of concept code. And for that code, we use a CRB driver, TPM CRB driver. We do not use that anymore. And it uses wolfSSL. Currently, we are using OpenSSL. Okay, we are booting the gas. And here you can see that OVMF is already able to found the virtual TPM and start recording measurements to the VTPM. Okay, the guest booted. The first thing I want to show is the PCR read. So we can see that the VTPM was found, the guest OS found the VTPM, and it was populated during the boot, all the PCR values. And also, the step you just saw is the EKPub. We have to get the EKPub the same way that the keylime expects. Keylime expects the EKPub in the TSS format. And this is the EKPub, 316 bytes. And welcome to my debug image. There's a lot of debugging messages because that's the only thing we can do when we are debugging a confidential virtual machine, because it's encrypted. The memory of the guest is encrypted. And then we get the attestation report also by reading the TPM and copy the attestation report and the EKPub to the host. Simulating a remote attestation, but it's not remote. And here we run, I run this validate SVSM-vTPM Python script that basically follow those steps that I mentioned, which is basically check the signature, download the key from the AMD website, check the signature, and then check the content of the guest. Okay, and this ends my presentation. And for conclusions, the SVSM, we have the SVSM-vTPM is protected from the guest. The VTPM data is protected from access coming from the guest OS and host OS. The EK is unique because it's generated randomly and it's authentic. The EKPub is authentic because we have the attestation report. And we have this ephemeral, which is a simple design, but it's enough for TPM-based attestation. And that's it. We are contributing it to the open source projects. We have time for questions? No? Okay. Thank you.